Thank you very much, Bernard, and thank you very much for all the panelists. I will continue speaking in Spanish. Muchas gracias a todos por la oportunidad de estar en este prestigioso panel. Como ustedes sabrán, América Latina y Europa estamos participando
Latin America and Europe
y eventos a través de diferentes posibilidades. Uno de ellos va a ser el próximo panel que tiene que ver con infraestructuras de investigación, con el objetivo de buscar puntos en común entre ambos países y, por tanto, celebramos la realización de este evento y agradecemos en nombre de todos los países de América Latina y el Caribe, que también formamos la Red Latinoamericana y Caribeña de Puntos Nacionales de Contacto para el programa Horizonte Europa, la posibilidad y la pertinencia de este evento. Nos acompañan con nosotros 4 excelentes panelistas. El primero es el profesor Jose Roque. El profesor Jose Roque es graduado de la Universidad Estatal de Campiñas y tiene a su vez un doctorado en física por la Universidad de Berkeley. A su vez es catedrático de la Universidad de San Pablo y desde el año 2018 es director general del Centro Nacional de Investigación en Energía y Materiales en Campiñas, Brasil. Muy bienvenido, and the floor is yours, please.
Well, good morning and good evening.
Buenos días, buenas tardes a todo el mundo. Gracias, Claudia.
Screen here with my presentation. Okay, let's hope everything works fine. Okay, can you see?
Yes.
Okay, now it's full screen?
Yes.
Okay, thank you. So I'm going to briefly talk about CNPEM, the Brazilian Research Center in Energy and Materials. As Claudia said, I'm Director General since 2018, but I have been in the center since 2009. I was Director of the Synchrotron Light Source National Lab, and the major project of the center starting in 2009 was the construction of a new synchrotron light source, which is Sirius. You see a picture over there. So CNPEM has, of course, as its sort of major infrastructure, the synchrotrons, but they are not the unique infrastructures or activities in the center. So we have 2 synchrotrons in the center. The first one was the very first synchrotron in Latin America, actually the very first synchrotron in the Southern Hemisphere, UVX. It was a 2nd generation light source, and it operated until the end of 2019 when Sirius started its activities. So you see a picture of the old synchrotron down there. But we have also nanotechnology labs, concentrated, most of them concentrated in the buildings that I'm showing here in the right of this picture. It has the, let's say, the most sophisticated set of electron microscopes in the country, some of them quite unique in cryomicroscopy, but also other, let's say, infrastructures for manipulating and, let's say, producing nanomaterials with clean rooms and many other techniques. Then we have, let's say, a large complex of biosciences, biotechnology, and biorenewable labs concentrated in sort of in the middle of the campus of CNPEM. It has many facilities for structural molecular biology and other biosciences techniques. And it goes all the way to a pilot plant for a scalability of processes and interacting more closely with the industrial sector. And a quite unique, let's say, capability of the center is a large number of competences or groups in engineering and scientific instrumentation. All this competence was derived from the construction of the synchrotron light source since the very first one. And we have not only a variety of groups, but many installations for analysis and fabrication of components. We are a private nonprofit organization, and we have a contract with the Brazilian Ministry of Science and Technology and Innovation. And so we operate under, let's say, not the same rules as the let's say, direct entities of the state, but we operate with a contract with the government. We have about 660 employees, counting technicians, researchers, engineers, and the support staff. And if we count trainees, postdocs, students, and outsourcing is about 500 more people. So we have, on regular days, about 1,200 people circulating in the campus. Of course, now in the pandemics, this is not happening. We have a smaller fraction. And we organize all these activities in 4 national labs connected to CNPEM, the Synchrotron Light Source National Lab, the Biosciences National Lab, Biorenewables National Lab, and the Nanotechnology National Lab. Each one of them has its own director. You had the opportunity yesterday to hear 2 of them talking, the Synchrotron Light Source National Lab Director and the Biosciences National Lab Director talking about their some of their activities. This gives, let's say, a very quick overview of the evolution of the campus in this almost 30 years of history. It started, the main goal was the construction of the first light source, and then all these other activities that I have just described were incorporated through these 30 years. And in the bottom here, I show a little bit the evolution of the synchrotron light source, the Sirius construction, starting the building itself started to be constructed in January 2015. Most of these facilities, they operate as open access facilities, and we receive a lot of researchers on, let's say, normal years, not during the pandemics. We receive more than 1,500 researchers every year on the campus, and a large fraction from abroad, mostly from Latin America, about between 12 and 15% of researchers from Latin America or from abroad, they come to the center. So, especially because we have the only synchrotron light source in the, as I said, in the Latin America, and some of the unique electron microscopes also in the country. An example, for example, the usage of the cryo microscope and interaction between the internal national labs. This was a recent publication of the Maiaro virus. It's an important virus here in this region, and showing the capability of producing this virus and making the observations in the cryo microscopes, not to talk about the synchrotron only. Of course, the most unique infrastructure is the synchrotron itself. Sirius was built to be a very competitive synchrotron light source. When you look at the what you have in the world, is one of the first 3 4th-generation light sources. So it changes completely the capabilities of this region concerning what kind of experiments one will be able to do here. And also it will have an important, let's say, it will be very relevant for this cooperation between Europe, of course, but other areas as United States and Asia, etc. Because now we'll have, let's say, a comparable equipment as one can access in these other places. Sirius is placed, is housed in a building of 68,000 square meters. The building itself is a very special construction. We say that the synchrotron starts 15 meters below ground because, let's say, it needs to have a very special floor to actually house the accelerators and the beam lines. Inside the building here, you have the accelerator tunnel. Inside the tunnel, you have the LINAC, then the transport line, then the booster in the inner wall, and then the storage ring. And then you have exiting here the beam lines. It's a 3GeV storage ring with a very small emittance, and we'll have a tour inside the ring. So here is where the electrons are first generated and then accelerated in the linear accelerator to 150 million electron volts. Then it's transferred to booster. In the booster, their energy is increased to 3 billion electron volts, 3GeV. Once they have reached this 3GeV, they will be transferred to the main ring, the storage ring. We have 20 sectors similar to the ones you are seeing here. So 20 equivalent sectors. It's the synchrotron light source. You collect them on the front ends of the beam lines, and then you go out of the tunnel to the beam lines. And at the end of the beam lines, you'll be able to do your experiments. So as I have mentioned, here is a picture of a beam line here on the left. And Sirius will be able to have, once fully occupied, up to 38 beam lines. We are starting this, let's say, construction phase, with a set of 14 beam lines divided in phase 1A and 1B. The phase 1A has the beam lines, let's say, highlighted in red. There are 6, total of 6, but we are also trying to finish in Buia, which would be one of the phase 1B beam lines, to be actually also finished by the end of this year. So we hope to have by the end of this year 7 beam lines on different stages of scientific commissioning. They will cover a large variety of, let's say, research areas. We structure in 3 major research areas: soft and biological matter division. We'll have 6 beam lines that will be mostly dedicated to these areas. Of course, other beam lines can be used interchangeably in other fields, but these will be the main scientific, let's say, cases for these 6 beam lines. So we have coherent imaging, able to do 3D structures of cells and similar objects. We have the Imbuya, which is the infrared beam line, important for a spectra of biomolecules and other systems. Manaka, which is the first one operating for structural molecular biology. The Sapucaia for small angle scattering, but not coherent imaging. Caterete will be able also to do small angle scattering, but the idea is for coherent imaging. And the Cedro it will be important for secondary structure of proteins. It's circular dichroism of macromolecular biologists. These 2, Manaka and Caterete, are phase 1, but as I have mentioned, in Buia, we will try to finish by the end of this year as well. Then we have beam lines that will be important for materials that are heterogeneous and hierarchical. For example, like soil, cement, and things like that. So we'll have Mogno is a high energy beam line. We'll be able to do, let's say, tomography on micro and nanoporous structures, so important for soil, rocks, cement, and similar materials. And we'll have 2 experimental stations will allow experiments with resolutions between 100 nanometers and 10 micrometers. Jatobá will be mostly for study of disordered materials, amorphous materials, for example. Quati will be important for studying the local chemical structure, so it's a spectroscopy beam line. Carnaúba is our most, let's say, sophisticated beam line from the point of view instrumentation. Will allow measurements in tomography and also fluorescence of systems with resolutions up to 1 nanometer in its end. The longest end station is about 150-meter beam line. And Paineira will be important for crystallographic studies, especially powder diffraction. Phase 1A has Mogno and Carnaúba. Finally, mostly for condensed matter and let's say quantum materials division, we have EMA for extreme conditions, will allow, let's say, high and low temperatures, very high pressures, and high magnetic fields, will allow the exploitation of phase diagrams under, let's say, extreme of many different kinds of external conditions, important for geosciences, planetophysics, or investigate.
To alert you about the time.
Okay, I'm finishing. Then RP is for electronic structure, sub-IA for magnetism, and EP for, let's say, charge collective dynamics. Manaka just did the first experiments on July 11th of last year, received the first external users in September, and now is open for proposals. Anyone can submit proposals, just enter our webpage. This was an important project also for innovation. We interacted with a variety of industries in Brazil. So a project like this of research infrastructure not only does great science, but also impacts the innovation of the country. Well, thank you very much. And I'm open to questions